Good morning, everybody. My name is Derek Landwehr. I'm with the Barton Technology Center based out of Watertown, Wisconsin. And today I'm going to be talking about testing for thermal spray coating adhesion via the instrumented strain gauge measurement during 4-point bending. So this is some work that's been completed over the last few months by myself, my colleagues at Barton and Thermal Spray Technologies, Daryl Cromer, Beth Aprovich, and Jim Watts. So first start out pretty simple, going through some of the basics of adhesion and the current test methods that are being used. And then I'll get into our 4-point bend test method using strain gauges and how we're actually looking at coating adhesion through that method. And then really get into the results in the experiment, directly comparing the C633 adhesion test results and compare that to our 4-point bend test method. So thermal spray coating adhesion, I'm sure everybody knows all about this here, but ASTM defines, or ASM defines that as the interfacial bond strength or the attractive force between solid surface and second phase, and also the manifestation of the innate interatomic and intermolecular bonds. So thermal spray coating interface there of an HVOF coating on the substrate. And the mechanisms of adhesion are through diffusion, chemical reactions, and van der Waals forces. So there are many different test methods that have been used and proposed over the last several decades. And basically all these tests have different approaches to applying the force between the coating and the substrate in order to basically take the coating off of the substrate. So there's a list of them here, but today I'm really just going to focus on comparing to ASTM C633, which is the direct tensile pull-off method. And that's the schematic here. Really this test, simply put, you're putting uniaxial tensile stress from the coating after applying an adhesive to the surface and then pulling directly vertical. So that's a force normal to the coating surface. And this is the most common test done in industry for qualifying a thermal spray coating and process. We do know of quite a few pitfalls of this test method. Every aspect can create variance in the process and in the test. Everything from the method that you use to cure it, to the geometry and how you're fixturing the parts as they're actually cured, curing the adhesive. But we are going to compare this test to our 4-point bend just for a comparison. A key point to ASTM C633 is really the significance and use that they discuss in the standard here. And it states exactly that it's recommended for the quality control or acceptance testing. And it's used to develop or qualify a thermal spray operator's equipment. So from that statement, and then also the statement in 3.2 here, it's really saying that the ASTM C633 data cannot be used from a technical standpoint to base a coating design for a certain application. And really we've seen that through our experience with the 4-point bend method and some other data that we've seen, that C633, the limits of that test are not representative of what you can actually achieve with a thermal spray coating in actual service. So that's really the key point of why we looked at an alternative test method to C633 to really consider the true engineering criteria and true engineering behavior of these coatings. So as I mentioned, we've seen through literature already published data that does show that thermal spray coatings can function beyond the limits of C633. So C633, the adhesives that are used, we do see that there are limitations of about 10 to 13,000 psi in the actual adhesive that's used. And in some cases, the coatings do basically last, the adhesion lasts up to that adhesive strength, and so you really end up not knowing how strong that bond is. So this is one example of data that was previously published by Lemko and also Daryl Cromer at Battelle. This is through a constant radius cantilever beam test. And so basically this is It's a fairly complex alloy, aluminum, nickel chrome, multi-layer coating applied to Haynes 25. And with this loading up to 2,000 microstrain, and that's 2,000 microstrain basically right at the coating interface, that is showing, because of the Haynes 25 alloy, we are seeing that that adhesion strength is well beyond the C633 limits, as the 2,000 microstrain correlates to about 65,000 psi. So that's one example there. That was testing down at room temperature. Now another example here, data from Brandt that was published in the Journal of Thermal Spray about 20 years ago. This is fatigue type testing. There's several coatings there, but the 8610-4, which will also produce data for at about 100 cycles, that's lasting to about 250 megapascals, which is about 45,000 psi. So another example there, again, different loading scenario than C633. Again, that's uniaxial tensile loading. Now this is fatigue type testing, a little bit more representative of what's seen in the field. And there's example data of what can be accomplished with these thermal spray coatings. So what is our motivation? Really, we saw that C633 was not representative of in-service conditions. So really we wanted to develop a test within Fisher-Barton at our technology center for our divisions and our customers to be able to utilize some of this data to understand the true behavior of these coatings. So again, it's more representative for in-service conditions, has greater sensitivity than C633, and also has less variability. There's been numerous studies done on C633 that do show quite a big range in some of the data depending on the process. And so that's what led us to the 4-point bend test. So fairly simple geometry. We have a 12-inch by 1-inch by 1/4 inch 1018 steel substrate, and then we apply the coating on the bottom side on one side of the bar, and then that side to put the coating under tension, that's going to be put on the bottom side of the bar, and as that stress or as the force pushes down, that's putting the coating under tension. And then we have a strain gauge that's going to be applied to the surface of the coating. And the strain gauge is how we're going to truly understand if is still adhesion or if at some point we've lost adhesion. But then also we'll see that the strain gauge can allow for other behavior to be understood at the same time. So the 4-point bend test is pretty simple fixturing. And then we're using our MTS 322 load frame to measure force, displacement, and then from the strain gauge, look at the voltage data, and so we can show the strain at the coating surface. So our coatings are comparable to the ASTM C633 approach at about 15 thousandths thick. So for us to actually calculate the stress at the interface, we're using beam theory and the flexure formula. And so real quick, as that beam is bent downward, we're putting the bottom side of the bar under tension and then the top side under compression. And so the stress that we're calculating is right here at the interface between the coating and the substrate. And then our strain gauge is then applied at the surface of the coating again. So there's a little bit of a disconnect there as far as our strain is not at the exact same location. But again, we're using the strain gauge to show if there's adhesion or lack of adhesion at some point. And because of our pretty simple geometry, the beam theory equations also are fairly simplified to the moments over the cross-section stiffness. So fairly simple math. Now our approach right now, we're assuming that it is a single body. And so basically the substrate properties dominate in this scenario. Beam theory is also only applicable only until the yield point of the substrate as far as the math, and I'll show that discontinuity there as far as when that yield point hits. And then the reason why we use 4-point bend over 3-point bend is that there's a constant radius between the upper force components. So that allows us to have more flexibility with our strain gauge positioning, and then we have constant stress along that radius. So in order to actually detect if we have adhesion or not, we're applying linear strain gauges to the top surface of the coating. So you can see the coating is applied not across the full width of the sample, as we wanted to reduce any edge effects, and then our strain gauge is in the middle of that coating patch. So we're using strain gauges for micro measurements. It's a linear strain gauge that's meant for basically the thermal expansion is matching the substrate in this case. So the gauge selection does play a role in this as well, depending on what substrate you're using and what temperatures you're running. It's applied by the micro measurements M-Bond 200, and then we're using a strain gauge conditioner and amplifier system to actually process the data to convert voltage to strain. So our test matrix here, really this is a side-by-side comparison. We sprayed the same materials and the same process for ASTM C633 tensile pulls and our 4-point bend. So we have aluminum bronze sprayed by electric arc spray, alumina sprayed by atmospheric plasma, and 8610-4 sprayed by HVOF. So with C633, these are the standard tensile bars here, tensile pulls. So 3 examples here. With the aluminum bronze, we had a cohesive failure. That coating failed completely within the coating and not at the interface. In comparison to the alumina coating in the middle there, we had complete adhesion failure. So that coating did delaminate at the interface. And then with the tungsten carbide cobalt chrome 8610-4, that was 100% adhesive failure. So that one outlasted the adhesive strength itself. So looking at the data here, aluminum bronze about 6,000 psi is a fail point of the cohesiveness. Alumina was at about 1,500 psi. And then again, as we mentioned, 8610-4, in comparison to the 2 adhesives that are there in blue, the adhesive that was used, the 2086, in all 3 cases, the adhesion strength under tensile normal loading conditions basically was all due to the failure of the adhesive itself and not the bond strength. Comparing this to a 4-point bend test now. So this is what a typical curve will look like. So with the dashed line, the lower dashed line, that shows nice, if that's the microstrain that's recorded from our strain gauge, that shows very nice tracking as we get, essentially as that displacement bends the bar down at a constant rate, we should see a constant strain rate. And that's what we see in this aluminum bronze sample. And then our calculated stress at the coating substrate interface then follows the dark line up to the yield strength of the substrate. Again, 1018 steel substrates. That was about 80,000 psi in this case. And basically, we have constant strain well beyond the yield point of the substrate. So this is showing us that we have coating adhesion well beyond the yield point of the substrate, as opposed to what C633 was telling us under the different loading conditions, is that it was well beyond or well below 10,000. This shows us quite differently under these loading conditions along the length of the interface. With the atmospheric plasma sprayed alumina, we have a similar type curve here, but there is a little bit different behavior when it comes to the strain on the lower line there. Not quite as linear as the last set of data. And we think that, although we haven't studied it, we think that's some other behavior going on with the coating, where essentially you are having some splat boundary sliding that then results in non-linear or non-perfectly linear strain as that displacement progresses. But still, in this case, the substrate yielded at about 60,000 psi in this case. We do have coating adhesion still well beyond that yield strength, and again, well beyond what C633 might tell you. A little bit more interesting data here in the HVOF tungsten carbide cobalt chrome. Not linear, and we also see these jumps and these dips in the strain. And so what that signifies to us is that there are coating cracks, and really it's a confirmation of coating cracks as we could audibly hear them during the test. And so as you see a drastic increase in the strain, that's going to be a crack directly under the gauge, and then a drastic decrease in strain is going to be a crack just outside of the gauge area, basically stress relief. But again, this is the last case of that the coating adhesion is well beyond the yield strength of the substrate, still above the ASTM C633 limits. So that's really the main takeaway from all of this data. Now it is different loading, but this is closer to true functional behavior from our perspective. And this is just confirming we do see some of those cracks looking at the top surface of the coating after the test. Now we did one test where we basically flipped the bar to put the coating under compression, and this is one example of when we do completely lose adhesion, basically the drastic drop in strain there at about 0.4 inches. That's basically when the coating completely flaked off, and that's what the example would be if we did lose coating adhesion. So some considerations for 4-point bending in general, versus C633, some of the things you might have to consider here. Applying strain gauges, it does take some practice and some care. This isn't just putting some glue on and putting the gauge on. There's some pretty careful sample preparation and surface preparation to get that gauge to adhere properly. Using strain gauges does require additional data processing, so you can convert that voltage and get it into strain. So there's some extra equipment there. And as I've shown here, the tests don't always produce failure. There's going to be a relationship between your substrate material and when that yields and what the coating can withstand. But like in this case, in those 3 examples, we didn't show complete adhesion failure. And then using strain gauges, it also opens the door up for further interpretation of results. So it's not just spitting out a number, but you're really looking at the behavior of the coating overall. So that does require some expertise in the tests and in the system that you're working with. Really the main advantages that we see with the 4-point bend method is that it is more representative for industrial applications from our perspective, as opposed to C633, which is pulling normally to the surface. That's just not very common from what we see. This test does open it up for multiple loading conditions under tensile, compressive, or fatigue loading. And with those different loading conditions, you can have different strain gauges to look at the stress in the different orientations. We're not limited by the adhesive strength as you are with C633 from the strength standpoint and also temperature. So different strain gauges could be used for higher temperature testing if that's your application. As we've shown with the strain gauge sensitivity, we can look at other deformation and cracking. And there's been other research by other folks using acoustic emissions to detect other cracks beyond the strain gauge. So the test method, although it can be complex, it can be simplified. You can get a lot of data, a lot of valuable data that can be used for true engineering application. So that, thank you for your time today. I'm glad to take any questions here.